Use statistical technique deal with group differences. The first question that we will ask is, are differences reliable, significant? Then, what is the second question? It is, are differences, if significant, meaningful? What do we see in the literature? More and more, meaningfulness is being addressed. When reporting meaningfulness, we might ask how much of the variance in the dependent measure is accounted for by the independent variables. Generally, we use omega squared or effect size to represent meaningfulness. Omega squared is the estimate of the strength of the relationship between the independent variables and dependent variables. Total variance is the sum of true variance and error variance. Omega squared is ratio between true variance and total variance. When we talk about power, please look at formula for t-test. I would like to ask two questions regarding power here. What is it? Probability of finding differences when they exist. How do we increase it? Use strong treatments, administer those treatments consistently, increase number of participants, decrease variability among subjects, change alpha. Use an appropriate research design and statistical analysis. If we have more than two groups. For example, if we have three groups, how many t-tests are needed? Do we run 3 t-tests? If we have 4 groups, how many t-tests are needed? Do we run 6 t-tests? What would happen with multiple t-tests? For example, in the example 40%, 60%, 80% intensity program, why not do a t-test between 40% and 60%, a second t-test between 40% and 80%, and a third t-test between 60% and 80%? The reason is that this would violate an assumption concerning the established alpha level 0.05. In other words, we inflate experiment-wise error rate by conducting multiple tests. The alpha level increases exponentially. Thus we may increase the chances of making a type I error. Then, what should we do? We should run ANOVA. Simple ANOVA allows all 3 groups to be compared simultaneously, thus keeping alpha at the designated level of 0.05. ANOVA is analysis of variance. It is a statistic to test for overall group differences between more than 2 groups. It is an extension of the independent t-tests. In fact, T is just a special case of simple ANOVA in which there are only 2 groups. You can go to page 160 and do the example. In fact, we can get the ANOVA table from SPSS or SAS outputs. In ANOVA, we sometimes need to conduct follow-up or post-hoc tests. Follow-up or post-hoc tests are used to determine which groups are actually different from one another. Several follow-up tests protect the experiment-wise error rate or type I error. These methods include Chef, Turkey, Newman-Cools, Duncan, and several others. In the behavioral science, we generally recommend the SCEP follow-up. It controls type I error for any number of appropriate comparisons. F-test controls for experiment-wise error rate. F-test is still that ratio between true variance and error variance. In simple ANOVA, T is a special case of F when there are only 2 levels of the independent variable groups. In fact, this relationship T square equals F is exact. You can check this in any ANOVA table of the output. Factorial ANOVA is analysis of variance in which there is more than one independent variable factor. Theoretically, a factorial ANOVA may have any number of factors and any number of levels within a factor. However, we seldom encounter ANOVA with more than 3 or 4 factors. Main effects is tests of each independent variable when all other independent variables are held constant. For example, in 2 by 2 ANOVA, there will be 2 main effects and 1 interaction effect. You might refer to text example on page 163, there were 2 levels of intensity and 2 levels of fitness in the example. Factorial ANOVA can determine the combined effect of 2 or more independent variables, or how the effect of the levels of independent variable A change across the levels of independent variable B. Regarding the interaction effects, what happens in one independent variable depends on the level of the other independent variable. Treatment effect one independent variable has on the dependent variable is not the same for all levels of the other independent variable. In essence, it makes little sense to evaluate main effects when the interaction is significant. When evaluating the interaction, we can plot the interaction and describe it. Please remember that, when the interaction is significant, follow UPS on main effects are usually unnecessary. Repeated measures ANOVA is analysis of scores on the same individuals on successive occasions, such as a series of test trials. It is also called split plot ANOVA or subject by trial ANOVA. In repeated measures ANOVA, each subject acts as his/her own control. The simplest form of repeated measure is dependent t-test. That is, dependent t-test is the simplest case of repeated measures ANOVA. Advantages of repeated measures ANOVA include 1. They provide the experimenter the opportunity to control for individual differences among subjects. 2. They are more economical in that fewer subjects are required. 3. They allow study of a phenomenon across time. The problems of repeated measures ANOVA include 1. Carryover effects. 2. Practice effects. 3. Fatigue. 4. Sensitization. Variance is called ANCOVA. It is combination of regression and ANOVA that statistically adjusts the dependent variable for some distractor variable called the covariate. Covariate is a distractor variable that is statistically controlled in ANCOVA and MANCOVA. Analysis of covariance controls for differences that exist that could affect the results of the study. ANCOVA can be used in factorial situations and with more than one covariate. Bonferroni technique. Sometimes researchers make several comparisons of different dependent variables using the same participants. Usually a multivariate technique is the appropriate solution. If we use multiple ANOVA for each dependent variable, it results in increasing the alpha that has been established by the researchers. One of the solutions is appropriate for adjusting alpha. We call Bonferroni technique, which simply divides the alpha level by the number of comparisons to be made. The second option is to leave the overall alpha at 0.05 but to calculate the upper limit that the alpha might be. Multivariate cases have one or more independent variables and two or more dependent variables. Multivariate techniques often used in experimental studies are discriminant analysis, multivariate ANOVA, multivariate ANCOVA. We use discriminant analysis when we have one independent variable, two or more levels, and two or more dependent variables. The technique combines multiple regression and simple ANOVA. That is, discriminant analysis uses a combination of the dependent variables to predict the levels of the independent variable. Use MANOVA when we have two or more independent variables and two or more dependent variables. MANOVA is a rather straightforward extension of ANOVA. The only difference is that the f-tests for the independent variables and interactions are based on an optimal linear composite of several dependent variables. There are several ways to obtain f in MANOVA: Wilks lambda, Valais trace, and etc. We usually use the f for Wilks lambda. We can also conduct MANOVA with repeated measures in some cases. I would recommend you to take an advanced statistical course if you have interest in this area.